filter is of X. Now, narrowband noise, the power spectral density of narrowband random process is non-zero only in a narrow frequency band, which is very small compared to the central frequency Fc as shown in this figure. Right? The narrowband noise, the power spectral density of a narrowband noise is non-zero only in a narrow frequency band, which is very small compared to the central frequency. Right. It is convenient to represent the noise, narrowband noise random process in terms of in phase and the quadrature component. Right. So we have done that in chapter 5, right? In phase, there was a question in the exam as well. Right? Just write down the in phase and the quadrature components, right? There was a question, so I'm just talking about the same thing here. So we can represent the narrowband noise in the in phase and quadrature. So in phase is the cos and the quadrature is the sine, right? Okay. Now the PSD of a quadrature noise component XC and XS are given by this. Well, both are same, both are equal. So here is the in phase and in phase and quadrature component power spectral density, which is equal to g of x f plus fc plus g of x f minus fc, where g of x is the PSD at narrowband noise. Consider the noise n t obtained by passing white Gaussian noise with spectral density of n by 2 through an ideal band pass filter, right? And assume that fc, the central frequency, is much larger than 2 times b, right? Where b is what? Here is b. Right? So here nt can be expressed in terms of, right? So here we are representing nt, which is basically the quadrature component and the in-phase component. Here is the spectral density of the quadrature components, right? So this is g of x, this is g of x f minus fc, right? So we are moving in back, we are moving in this direction, and similarly in advance, we are moving in this direction. This will be g of x f of x, and together, what is g of x t and g of x y? This is what it is, right? So this would be the g of x c and g of x quadrature. Now, the spectral density of NC and NS are obtained like here. G of NC is equal to G of NS. What is C is quadrature, right? So we can represent NC and NS spectral density as equal to this. It is equal to N for this frequency, F, which is smaller than or equal to B. So here we can represent that, as you notice here, right? Now this N here, this is G of NC, G of NS, this is G of NF, and if you here, N, what is this N? If I want to find the power, right? The power here, N squared, that is equal to 2 times Fc minus B, Fc plus B. Now again, the question is here 2 times Fc minus Fb, Fc plus B. Again, symmetric property, that they are symmetrical, even symmetrical property. So you can use those that too, right? So you can integrate that from Fc minus Fb, Fc plus Fb multiplied. So that too, because both are equal, both are even, right? Both are even, so I can take this one, I don't need this one. If I, for this and this they are equal, that's why I'm multiplying it by, right? So I'm integrating it from Fc minus B to Fc is the mirror image, right? So I can do that. So that's why this tool is here. So when you solve that, right, here you will get the quadrature, right? The n and c power is equal to 2 times NOP, 2 times NOP. This is the power for n, and these are the components, right? 2 components power. So we can get the power of both components as 2 times NOP. And that's it. So let's chapter. Okay, there is no homework for chapter 6. Okay, this week no homework. Yeah, good, right? Yeah, so no homework this week. Chapter 5, chapter 6, because you have already done that. I'm not giving any homework for this. I'll give chapter 7. We'll start. Oh, great. Is this one? This one? 7? Okay. This one probably? This one? No? This one? Where is the? Yeah. Sure. Okay. Yeah, okay. So, well, let's start chapter 7, right? Well, there will be homework, but after 1 week, not now. So this week, just relax. There's no homework. Right, well, before we start this chapter, chapter 4, chapter 5, we did not consider noise, right? We say, okay, we have a signal, right? We have a signal, we want amplitude modulation, we want frequency modulation, we want phase, right? That's what it. We did not consider the noise. Well, of course, in nature, well, when we are transmitting a signal, right, the channel will add noise. So now we need to consider what's the effect of noise on the signal. Right? What will happen? So now comes, well, remember SNR, signal to noise ratio, right? Now we will talk about that in this chapter. How noise is affecting the signal quality, right? So here is that. So before we define, before we see the noise, effect of noise, we want to first define 2 terms, which we'll be using again and again. One is CNR, right, carrier to noise ratio, and one is SNR, signal to noise ratio. So what is carrier to noise ratio? Defined as the ratio of carrier power to the noise power, right? Carrier power to the noise power in a specified bandwidth, usually measured using a spectrum analyzer. In the lab, you measure it using a spectrum analyzer. If you go to lab, you will see that spectrum analyzer. And then this is basically pre-reduction measurement on carrier modulated waveform before we do the deduction, right? Before we do the deduction of the modulated waveform. And then what is signal to noise ratio? Well, ratio of the signal strength and signal power to the noise power, right? Made at the baseband before modulation or after deduction or demodulation. After modulation, right, we do that signal to noise ratio. So these 2 measurements we'll perform in our analysis when we talk about the noise. Pre-reduction measurement is what include noise contribution from the camera, modulator, transmitter, inline amplifier, and demodulator receiver. Ideal for characterizing end-to-end performance, overall signal quality. Overall signal quality. in baseband signal, right? Noise performance of the baseband signal. Baseband signal, the message signal is transmitted without any carrier. Modulation as shown in the figure, right? So here is our message signal. We are passing it through the channel. Channel will add some noise, right? Then we have this low pass filter, right? And from low pass filter, of course, when noise is added, we pass it through the low pass filter. That low pass filter will give us the signal of this noise component. And since channel is assumed to be distortionless, well, we are assuming it to be distortionless, the output signal is an attenuated and delayed version of the message signal. Well, it's a distortionless channel, right? So if it's a distortionless, then it will give us an attenuation alpha, and then a delayed version, right? Where alpha and TD respectively represent the attenuation and delay introduced by the channel. So here is that baseband with the noise. So now the signal at the low pass filter is output of the low pass filter that is equal to this is the received signal RT that is equal to SO plus NI, which is equal to alpha ST plus NI. The output of the low pass filter, right? The output of the low pass filter is basically R1. That is alpha S dot T plus N. For Ni, this is Ni here. This is R1. Here we get R1, and here we get RT, right? And then here at the output filter we get this R1. R1 is alpha ST plus NO. The receiver output power, what is the output power? The expected value of this alpha square S square. The power spectral density of the noise at the low pass filter is given as minus infinity to infinity G of n, which is minus infinity to infinity n by 2 HR, which is basically equal to minus b to b, right? And why it's minus b to b? Because HR is 1 between b and minus b, right? So this is the power output. So here is that spectra at the filter input. So we have noise, incoming noise, well, this noise, right? And then we have this message signal, or it's a baseband signal. When we pass it through the filter, what we get this, right? So this noise is gone. So we are getting this message signal with the noise, right? With the noise. Now, what is the SNR at the receiver output? Well, this is the SNR at the receiver output, which is basically equal to the PR, received power, is divided by the noise power, right? So when you calculate, this is SNR, right? SNR output alpha square S square divided by NOB. This equation describes the SNR achieved with a simple baseband system in which all out of band noise is removed by filtering. Baseband analog fiber optic links are popular in video surveillance applications. So this is basically the baseband noise performance. Now let's talk about the AM, right? The AM, what is the noise performance in AM? Conventional AM, or let's start with AM. Message signal is stationary. Well, this is our assumption. We are assuming our message signal is a stationary, zero mean, low pass random process whose spectral density is band limited to beta. Receiver front end noise, Ni, is again another assumption. Receiver front end noise, Ni, is white sense, well, it's a WG, white Gaussian, with the power spectral density NO divided by 2. We assume, again, another assumption, we assume that the signal and the noise, they are uncorrelated, they are statistically independent. right? So we are assuming a lot of things, right? We are assuming a lot of things. We are assuming noise and the signal, they are independent from each other. Assumption. Now, the receiver front end consists of a band pass pre-deduction filter, which is typically the intermediate frequency filter in a super heterodyne receiver with a bandwidth 2G, right? This is the pre-deduction filter before we demodulate the signal. So we have this filter. Now, what is my received signal? My received signal RT before the filter is the signal plus the noise, NR. We are calling it NR, right? So now, here, what will be my R1? R1 is when I filtered the noise and the signal together. So let's say we are now let's say we are talking about a double sideband suppressed carrier signal. Remember double sideband suppressed carrier signal? So this is the expression, right? This is the expression for the double sideband signal. AC cos 2 for AC SFT signal times cos 2 pi ft plus this phi. You can ignore this if you want. You don't need this, right? So if I ignore this, I'm okay. Anyway, this phi is not playing any part in when I do calculation. You will see that it's not helping me anyway. But let's say we are not ignoring it. The message signal is again, we are saying message signal is stationary. It's a zero mean, low pass random process whose spectral density is band limited to the Hz. This phi represents uncertainty about the phase of the carrier waveform. But if we can ignore, we can. We don't need that in our calculation. Channel output signal is a derivated version of the transmitted signal, which is received in the presence of WGN. So what it does mean, it means we have a signal here, right? That is double sideband suppressed carrier DSP, double sideband suppressed carrier DSP SC. Channel will add some noise, right? So that noise, we will get the signal at the output of this, well, at the input, we will get a signal ST, which is double sideband, plus this noise at the input of this filter. Now we need to pass that signal through the filter. So here is that RT, right? So you have this signal, which is double sideband suppressed carrier, plus the noise, right? NI. NI is the noise. Here, assume that this angle, this theta, this phi is a uniform. So what is a uniform? Well, right, you know what a uniform is, right? It's uniform from minus pi to pi or 0 to 2. It's a uniform, right? So, and statistically independent of the message signal. So that means it is not helping us. If we can ignore that, we are okay. So I don't need to write this phi. If I'm doing calculation, I don't need to write this phi. This is not playing any part anyway. So well, let's say we are again assuming that this is uniform. Okay. Now let's find out the power. What would be the power of this signal? Well, expected value, no. Right? This is the power of this signal, right? Power of this signal. Here, this signal, power. This is the power. And now here, this is equal to this cos squared 2 pi ft plus this phi is half. How it is half? Cos squared 2 pi ft plus phi, it is equal to half. Well, what is cos squared theta? Cos squared theta is what? Cos squared theta. Cos squared theta is half and in the bracket 1 plus when you do that, when you take the expected value of cos, right, that will be 0. So you are left with half. So half plus half cos 2 theta, right? That's what cos square theta is equal to, cos square theta. Apply that formula. And when you take, when you solve it, right, when you solve this, put the values of cos square theta equal to, and solve it, you will see it will be equal to half. Some terms will cancel out, right? The constant term will remain half, the other term will cancel out. So you get to here. Now, here is our RT, R1T, which is the double sideband and plus this noise, right? Plus this noise. Now I need to pass it through the filter. What is S? Well, we know that S is average power in the message signal, and Ni has power spectral density of GF, and I have the noise power measured in the bandwidth of the baseband signal. And what is that? That is basically equal to NOB. NOB. Now we need to find out what is the noise performance, right? So first of all, we need to find out what is CNR, right? Channel to noise ratio. We call it CNR in. CNR in. So we need to find out that. So we know what is that, equal to carrier power at the receiver input divided by the input noise power in the message signal bandwidth. So we just find out it is alpha square A square AC square times the signal power S square divided by 2 times NOB, right? What are the assumptions? Prediction filter is an ideal band pass filter, right? What is the bandwidth of that? 2B. Therefore, the double sideband suppressed carrier signal is passed by the pre-detection filter without any distortion if the bandwidth is 2B. So now the pre-detection filter output R1 is equal to this here. This R1, right? This is R1. This is the pre-detection filter. Now we have here, right? Which is equal to this, and then simplify that. So what we are doing, we are putting NT. What is NT? NT is a narrow band noise which has 2 components, right? The quadrature component and the in-phase component. So we can represent NT by its quadrature and the in-phase component. We can, right? It's a narrow band noise. Where NC and quadrature component of the narrow band noise is mean 0 and variance of 2 times NOB. Now here is that spectra. Spectra at the pre-detection filter before and spectra after the filter, right? So here we had this spectrum, and then at the output of the filter we have this I'm talking about the noise, right? Now to coherently demodulate, R1 is multiplied with a carrier signal 2 cos. I need to get back the signal, right? How can I get back the signal? Excuse me. So, well, remember coherent demodulation, so I have to multiply that signal with cos, right? That carrier. So, if I do that, here I'm doing it, right? So, multiply that, R1 times 2 cos, and simplify. Right, so here is the simplification. Now, the filter will get rid of high. The filter will get rid of the high frequency term, the low pass filter, right? So it will get rid of all high frequency term, and it will give us this. It will give us. Now, you need to simplify that. You will get here. You will get some term here. Well, simplification, right? So some formulas are used. For example, cos square theta, right? So you will see here, this is cos, this is also cos, so cos square, apply that formula. What what is cos square theta equal to, right? 1 half, or half plus cos of 2 pi, 2 theta, right? Use that formula. So at the post reduction filter, low pass filter will get rid of those high frequency terms. At the end, you are getting okay. Notice here, this ns is also gone. Right? This ns is also gone. Ns is the quadrature component. This is also gone. So, and you are left with this signal plus the in phase noise component. In phase noise component. Post-reduction signal power. Now, what is post-reduction signal power? That is what the signal power is. Theory is equal to alpha square AC square times S, the signal power. Noise power at the post-reduction filter. Noise power at the post-reduction filter is given by here 2 times NOB. So the output reduction is basically SNR DSB is basically equal to this PD, the post-reduction power, divided by this power NC, right? And noise power at the post-reduction. So do the maths, right? So you notice here our SNR is equal to the CNR, right? Our SNR is equal to CNR, then the output of an SNR, the output SNR of a DSP system is equal to the receiver input CNR. SNR is equal to CNR, the figure of merit, but the figure of merit, it is equal to 1, both are equal, right? What is figure of merit? It represents how much improvement or how much no improvement, how much improvement is done, how much degradation is done as the signal moves from input to the output. How much? So this is called FOM, figure of merit. What is that? When you pass a signal through the channel and when it goes to the receiver side, how much power, how much SNR has improved or it has not improved. It's called figure of merit, FOM. And here in this case, it is equal to 1. It is equal to 1. Now, what is the noise performance of single sideband frequency? The single sideband. So here is the noise performance. So well, we know what is single sideband expression is. Here is the single sideband expression, right? So remember the signal, the Hilbert transform, right? So S, this hat is the Hilbert transform. And this phi represents our uncertainty about the phase of the carrier waveform. Again, if you ignore this phi, you don't need this phi in the calculation anyway. You don't need that. So you can even ignore that when you are doing calculation. You can just get rid of this phi. Okay. The channel output signal is, well, of course, when we pass this signal, this single sideband signal through the channel will introduce some noise. That is white Gaussian noise, and it is additive, right? So it is the attenuated version. Well, the channel output signal is the attenuated version of the transmitted signal, which is received in the presence of AWGN. So now the input to the pre-reduction filter, RT, that is equal to the signal plus the narrowband noise, Ni, right? Similarly, you can express Ni. Now, okay, so this is that RT. The signal power at the pre-reduction filter input is given by, well, power, right? So expected value of this, which is equal to here, the expected value of those. So when you simplify, you will get this, right? The expected value of the, well, these are constants, so you take it out. Now, expected value of those And now assume that this phi is again it's a uniformly distributed random variable, and it is independent of the matrix signal. So it is not helping me anyway. So well, let's see. We can simplify this equation. We can simplify this equation, right, like this. So this is basically expected value of S squared plus the expected value of the S Hilbert transform, which is equal to alpha square AC square S square divided by 4. Right, divided by 4. Now, the question is, how are they equal? How are they equal? Right? How are they equal? They this is 8, that is 4. How are they equal? What happened? What happened here? I'm saying this is equal to that. Remember when we were doing Hilbert transform, and we were having the properties of Hilbert transform. So a signal, right? A signal. If you take the Hilbert transform of a signal, the energy, right? The energy of the signal don't change. Right? Hilbert transform does not change the energy, right, or the amplitude of the signal. Hilbert transform does not change the amplitude or energy of the signal. So that means both are equal. Right? If both are equal, you can write down like this. So the receiver input noise is power measured in the bandwidth of the baseband matrix signal is given by this, right? And OP. The receiver input CNR is given by PR divided by PNI. So this is our CNR in, that is equal to PR divided by N not B. So just plug in the values, so you get this expression this way. Now the ideal pre-direction filter, whose bandwidth is equal to B, in the SSM AM receiver passes the upper or lower side band signal without any distortion while rejecting the out of band noise. The center frequency of the pre-detection filter is FC plus B by 2, where the sign depends on the choice of the sideband. Right. The pre-detection filter output is given by here. This is R1, which has this noise component. Right. So we can expand that. Similarly, we can also write down in here. So we are putting in this NC, right, which is basically the in-phase component, and similarly we can put the NS, which is basically the quadrature component of N. So here is that single sideband, the spectra at the pre-detection filter and the spectra at the post-detection filter. NC and NS are quadrature components of the narrowband noise with zero mean and variance and OB. To coherently demodulate R1 is multiplied with the carrier and low pass filter to recover the massive signal. Now at the output of the well, we need to here if we go back, we need to pass this signal here. Yeah. So here we need to pass it through the low pass filter to get back our signal. Which means we are demodulating that signal, so it will pass here. It will pass the, so here it will pass the, so 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 the other terms will be cancelled out. The filter will not allow other terms, so it will be cancelled out. So at the end, at the output of the filter, low pass filter, we get back our signal with this in-phase component, noise component, right? So that would be our now post reduction signal power PD, that is equal to um, alpha A square divided by P square S4. Noise power at the post reduction filter NC is NB. So while we need to find what is the SNR, well, SNR is the post reduction power divided by the noise power. It is the PNC is basically the power in the in-phase component. Just do that, right? Simplify it. So you again see here our SNR of the single sideband is equal to the CNR, the carrier to noise ratio. Right? They are equal. So therefore, what is the merit, figure of merit? The figure of merit again is 1, same as the figure of merit of the figure of merit of the double pass. Both are. So the output SNR of an SSB AM system, steam is equal to the CNR at the receiver input. Further observe that the coherent demodulation of both GSP and SSB signal results in identical SNR performance. Both are now let's talk about the conventional AM. In the conventional amplitude modulation scheme, the input to the pre-reduction filter, well, again, same thing is happening here. We have now conventional AM. So here is the signal conventional AM. Of course, RT is basically equal to the conventional AM signal plus the noise, right? And I. Now, just expand that, right? What is the signal power here? Well, signal power is the expected value of this, right? Which is equal to this, well, is alpha square AC square divided by 2, 1 plus MS square SN square. The receiver input noise power measured in the bandwidth of the baseband massive signal equals here. Well, we know that N times P. So what is the CNR? Well, CNR is the received power divided by the noise power. Right. So this is that power PR, and that PR divided by the noise power will give me the CNR N. Now I need to find what is SNR. Now the post pre-reduction filter output is given by X, well, the modulated signal, AM modulated signal plus this noise, right? So that is equal to that N noise. Well, we can break down that noise into its components, in-phase component, and the quadrature component. So we have added here. Now, conventional AM signal can either be deducted using the coherent reduction method, or we can also demodulate that signal using the envelope deductor, our choice, right? Whichever we want. So we can do both ways. So let's do the coherent demodulation. So here is the coherent demodulation. The demodulated output is given by this thing, right? Plus NC. So we have this DC term. Well, DC term is blocked out. So we are left with this signal alpha AC MA SN plus NC, right? Where NC is the quadrature component. Now, post-reduction signal power. Well, post-reduction signal power is given by this. What is the noise power? Noise power, well, NC is 2 times NOB. So just find out the SNRM of that. Well, SNRM is just do the mathematics. So when you do the mathematics, you get this S and Rm equal to the efficiency times C on Rm. Since this efficiency is less than or equal to 0.5, SNRM is at least 3 dB poorer than the output SNR of TSB and SSB system for the same CNR. So it is, well, we know that it is 3 dB poorer than the output SNR for DSB and single sideband system. We already know that the performance of AM is much poor as compared to the single sideband and double sideband. We saw that before in chapter 4. So what is the figure of merit? Well, the figure of merit is equal to this efficiency, which is what? SNR, signal to noise ratio, divided by the CNR, the carrier to noise ratio. It will give us the figure of merit. Here, the figure of merit is this efficiency. How much is the efficiency? That will give us figure of merit. Now, conventional AM, well, the envelope deduction, well, for the envelope deduction, the input to the envelope deduction again is the in-phase component and the in-phase component and the quadrature component, right? So the envelope, what would be the envelope of that? Well, the envelope of this signal is here, and what is the magnitude and the phase. Here is the magnitude, here is the phase. Okay, so I think we should stop here. How much time is left? 2 minutes? Yeah, so I think we should stop here. We'll start in the next class for the envelope detection. There's a long topic. Then we will have the high SNR, then we have the low SNR, high SNR, low SNR, so we'll do that in next topic. Do we have class on Friday or Saturday? We have class on Saturday? No? When our next class? No class? Do we have class on Saturday? No? No? Oh, next week, Monday or Tuesday? Monday. Yeah, okay.